With the backgrounds of electrical and optical properties of organic semiconductors, we are ready to discuss on the characteristics of OLED. Already I showed that this diagram several times, and usually OLED have at least 3 layers: Hall transporting layer, electron transporting layer, emitting layers. Holes are injected from anode and transported through HTL and reaches the EML. Electrons are injected from cathode and transported through ETL and reaches the EML, and they recombine to form extons and decay radiatively and non-radiatively. This energy diagram is almost similar as this homojunction LED structures, but this heterojunction structure, so this needs to be modified to have a heterojunction in inorganic semiconductors. To fabricate the displays, we need this kind of a very, very simple schematic diagram of display structures, where this is a PM OLEDs, passive matrix OLED, and this, let's say this is anode, and anode has this line electrode deposit at the organic layers, and then metal cathode, which is the cross direction, and the line electrode here. The voltage to this anode or cathode sweep from here to there and come back again and so on, so that with a frequency of 120 Hz or 240 Hz, so that here, and also at certain time, this is biased, for instance, and then you can apply the different voltages to get different charge injections, to get the different intensities of light and different colors of light, to get image in the line at a certain time, and the next time you get these images, this image again, line images. Then if you sweep this voltage rapidly enough, then our eye realize this image is just moving images. So this is the very, very, very simple schematic diagram of passive matrix display. If I introduce you this fabrication process in very rather short way, and patterning of this substrate, first of all, for contact, you pattern the chrome, and then you pattern ITO also, and ITO pattern and deposit chrome at the edge, and insulator formation with this shape, the patterns, and then you separate this and so on. And then you deposited HTL. This is the overhang structure, the separator, and then you deposit this organic layers and cathode. That means that you prevent a shortage of the electrode, because these are separated by these overhang structures, and then you get this kind of the electrode in this line and the anode along this line. After that, you encapsulate this device and dicing to get this kind of structures and the line here. This primitive passive matrix was fabricated a long time ago in my laboratories, and we just drive. You can see that this is very full, this is red okay, and so on. To get the colored images, we need to have a shadow mask. This is the case. You see shadow mask has this hole here in the very thin metal sheet, and then if you deposit this, put this one on the substrate and tab and evaporate organic layers, in this case blue emitting layer, and then only this part is deposited. In the next run, you just move it and open this part, green part, and deposit green, next one, and the red part. Then you can have this kind of RGB patterns using shadow mask. Still, this technology is in use for practical device fabrication, the display fabrications. Now let us move on to the light emission process in OLED using this schematic representation of an OLED on the applied bias. This is anode, and this is three-layer case. Here the electron holes are electrons injected and form to the emitting layer from extons by recombination of electron holes emit light. And so this is the process, and I show you that some potential of this anode and work functions and so on for this case. Now I'll discuss on the performance of OLED and which factors influence the efficiency and the lifetime of that. I don't discuss on colors because that depends on materials, and I just omit this chemistry part of materials. In order to understand the efficiency a little bit more, we need to consider the light emitting process using these diagrams here. Electron holes are injected and recombined in emitting layers to form extons. There are two different kinds of extons, singlet and triplet, with a ratio of 1:4. If we use just fluorescent light, just a singlet is actually recombined to emit light but decay. But if you phosphorate for triplets decay, that's we call the phosphorescent. And then emitted light must be outcoupled to outside of the device to be useful for display making images. The efficiency is usually expressed by external quantum efficiency. That's the ratio of number of photons emitted from the LED to the number of electrons injected to the LED. And if you just consider this process, you can think that the EQE, that's the photon number here out of injected electrons. Then you can write down the equation by this way. This is the extron formation efficiency. That means that the electron, how many extons are formed out of injected electrons. That's the extron formation efficiency. And then fraction of spin allowed extons. This, as I mentioned, there are 1:4 ratio, 3 ratio of singlet and triplet. If you use fluorescent molecules, you can have just the emission, the fraction of spin allowed exton is just 25%. But if you use phosphorescent dyes, then that can be 1. And also this radiative transition rates I explained already in the optical properties PLQI, which actually consider of the decay process, all the decay process, and then out of them, the only radiative decay are effective to get light. So that's called PLQI and then outcoupling efficiency. Some of the light is just trapped inside of the wave, this OLED without escaping from the OLED to air. So we can say this kind of one. So this is the internal efficiency times outcoupling efficiency. We say this by that way. Internal quantum efficiency can be the maximum 100% if we use the phosphorescent dyes or a triplet harvesting dyes, emitters, because by fabricating the device very well, you can get the extron formation efficiency to 1, and by getting the very efficient PLQI, the emitters with high PLQI, then you can also have a Q high here. So that's this internal quantum efficiency can reach 25% for fluorescent emitters and 100% by phosphorescent emitters. But outcoupling efficiency, we need to discuss a little bit more on that. And the current voltage luminous characteristics is the very basic, the most basic characteristics of the diode. And then this shows a typical JV and the light emission luminescence characteristics of an OLED. And under the bias voltage, under the built-in potentials, the current level is very small. Only diffusion current exists, and the drift current little bit increases with the voltage. So this is like that. But mainly diffusion current influence in this, this is ohmic current regions. And then the diffusion current region is near the this built-in potential range. After that, if you have this forward bias, you may get the space charge limited current region here. So generally, you expect this kind of JVL characteristics. Using these JVL characteristics, you can calculate external current efficiency because you have this photon number from this luminescence data, and you can get the current and the voltage using at a certain data point, and you can get this kind of EQE versus that. And sometimes the external current efficiency is reduced with increasing luminance. That is called efficiency roll-off. This specific device doesn't have much efficiency roll-off, but some of OLED and some papers show strong efficiency roll-off in some cases. And we need to understand what actually causes this kind of efficiency roll-off. I'll discuss a little in the later part of this device. Now let us discuss the factors influencing the EQEs one by one here, the external formation efficiency, and this spin around, and then PR quantum yield, and outcoupling efficiency, briefly. External formation efficiency can be understood from this one. You know, this is the ITO anode, and this is the metal cathode, and the whole current is injected, and the whole actually is the escape with this kind of the leakage current without recombination. And the electron also can have this kind of tendency. Then the external formation efficiency must be the recombination current divided by injected current. So injection current is just this current or this current, that must be the same here because continuity of current in the device. If that is not the case, charge accumulation must be taking place inside of that. So you have this, and the recombination current is the difference between this whole injection and the whole cases. Recombination charges, electron and holes must be the same, so you have this one. In order to have a recombination, the external formation efficiency to 1, J sub R must be the same, and in case this leakage current must be the same. That must be very simple. With just the simple thinking, this must be 0 to have a 100% external formation efficiencies. But if there is a leakage path, even though the whole current and the electron current are the same, still that can happen here. There's a poorly fabricated or designed devices. So we need a state here. We combine all this is electron density and hole density here, so that you can have this kind of. So this is hole density. This is electron density. So we want to have. In terms of consideration, it's very simple, but it is difficult to measure gamma directly from experiment because there is no way to distinguish hole current or electron current at a certain electrode. So instead of that, the direct observations, people just try to extract from the measured EQE, quantum efficiency, and the singlet, triplet, the emitter itself, and outcoupling efficiencies. So usually people do that by this way. So just extract this value by measuring this, and knowing this value, and the PR quantum yield, and outcoupling efficiency calculated. Then we just get these values. I'll show you in the later part. Now how about the PLQI? So Q part. We need to synthesize materials with the high PLQIs. Generally, rigid structure gives a high PLQI because of the vibranium motion is small, so that you can just push the singlet to just transition from singlet to triplets without the vibranium coupling the non-radiative processes. Also, you need to prevent concentration quenching that is coming from the intermolecular interactions of the same kind. And then usually there are also, of course, exceptional cases. But so in order to do that, people developed the doping technologies of the emitters in the host molecules. For instance, these red or green emitters are doped in these blue molecules here. And then there is no contact between red, the emitting molecules, rare cases, depending on the doping concentrations. Also, they design molecules to reduce the tendency to aggregate. Also, sometimes the purity plays an important role, so you need minute amount of metal ions, catalyst, for instance, and halogen, also the halogen molecules, bromine, and so on, and so on. So you need to purify the materials very, very, very well under the actually lower than the ppm order. So that's nowadays people develop the technologies and design the molecules to get almost 100% PLQI for red, green, and blue dyes, fluorescent or phosphorescent or the TADF molecule. How about the fluorescent dye or phosphorescent dye or the triplet harvesting molecules? The first work done by Jing-Tang in 1987 using the heterojunction thin film OLED, his group used this ALQ3. This is fluorescent emitters. At the time, they reported 1% EQE. Oh, that's quite high. Still, that was quite a high number, but it's quite low if we compare with the technologies nowadays. Anyway, IQ is limited to 25% because this is fluorescent molecules, and the triplets is converted to just heat. 10 years later, this group, these two professors in USA, reported this phosphorescent dye iridium complexes, that this molecule has iridium heavy atoms, and then they utilize the heavy atom effect to enhance the spin-orbit coupling, to actually enhance the phosphorescence rate, the transition from the triplet to singlets by spin mixing process. And then they reported that nowadays 100% PLQI is easily obtained, reported many times, for many molecules using these molecules now. And then 15 years later, other fluorescent molecules, but this time singlet triplet energy gap is so small, which has a donor acceptor structures, and the molecular orbital overlap between donor and the acceptor is small, so that the singlet triplet gap is small. And then in such case, you can easily convert the triplet to singlet by thermally stimulated delayed fluorescence, the conversion, thermally assisted delayed fluorescence. That's the short form of that. So that nowadays this can also allows the 100% IQE.